All right, so today we're going to be talking about conservation of energy. What does conservation of energy mean? We did talk about this in class just a little bit. What we're looking at is that it's always conserved, but it can change forms. What do we mean? Well, you saw that in the lab, the little PhET lab, where you could see that kinetic energy became gravitational energy. Sometimes if we have friction, it can become thermal energy or sound energy. So it can change all different forms, but you don't gain any or lose any. All right, so mechanical energy, we know, is going to be the total energy in a system. Now, how do we gain mechanical energy? Not gaining energy, brand new energy, but gaining energy into our system. Okay? So we gain mechanical energy when work is done on something. So if you do work, if you put work into a system, so if we have system here, and it has a certain amount of energy initially, and then we do some work, then what comes out is a final energy that is greater than the initial energy. Okay? Think about it. What would that work be? That work would be like a push, or on your car, feeding it gasoline so that it will make your car run faster. Okay, pressing on the accelerator pedal. All right, so now, total mechanical energy, if we look at it, is going to be the sum of your kinetic energy plus your potential energy. Okay? In physics on your sheet, this ME total is just usually referred to as E. Big E for total energy is K plus U. All right? Now, conservation of mechanical energy says that whatever you start with, your energy initial, has to be what you end with, energy final. Okay? That's when you only have conservative forces like gravity, system, then you conserve it. Now, what does this mean? Well, in terms of K and U, K initial plus U initial has to end up equaling K final plus U final. Now, does that mean that the K and the U stay the same? No, you may have converted some kinetic to some potential, or vice versa. Okay? Now, what if you don't have conservative? Look what it says. It says, while mechanical energy is not always conserved, total energy is always conserved. But not all energy is available to do work. All right, so what does that mean if it's non-conservative? If we have non-conservative work, usually we say work non-conservative, that is going to be, non-conservative work is going to be things like friction. Okay, things like friction, heat, sound. But if we think of this in terms of mechanical energy, what we find, though, still is what changes is our initial kinetic energy plus our initial potential energy plus whatever work non-conservative we see has to be equal to K final plus U final. Now, remember, work non-conservative is by nature going to be either negative, if it's like friction or sound, or if it's a push, it would be positive. So for negative, if it is removing energy, and positive if it is adding energy. Okay? So let's apply this conservation of mechanical energy here. We've got a roller coaster car with a mass of 250 kilograms. Okay, has a negligible speed at the top of the hill at point A. So what kind of, and it says shown before descending, find the velocities at point B and point C. So what we have to do here is we have to figure out our kinetic energy here is 0. Our potential energy, if you think about it, is mgh, isn't it? So this is going to be, to start with, our mechanical energy is going to be the mass, which is 250, times 10, times the height, which is 30. All right? So what is that going to be? Let me get my calculator out here. I'm giving you time to work along. I got 75,000 joules. Okay. So that should be without friction. And it says negligible friction, or a roller coaster with mass at the top of the hill. So it's not starting. So it doesn't say it has friction. So we're going to assume this is a frictionless thing. Okay, so find the velocity at point B and point C. So what we have to do is we know that the total energy, the energy initial, is going to equal the energy final in this system. So let's go from A to B. The initial energy at A, it had, if we do kinetic energy plus potential energy here, and then we do kinetic, so kinetic at A, potential at A, kinetic at B plus potential at B. Well, we know it doesn't have any kinetic energy at A, so that's 0. We know this is 75,000. Now, it's moving at the bottom right here. It has not come to a stop, so it is going to have kinetic energy, so that's going to be 1/2 mv squared here. And then it also, because it is not directly at the ground, it is also going to have potential, which would be mgh right there. So let's plug in what we know. We know it's 1/2, and this should be at B. Oops, I should fill in what I know. I know the mass, don't I? So the mass, which is 250 times v sub b squared, plus 250 times 10, and the height at that point is 10. And this is 75,000. So let's work this out. We're going to subtract. So we're going to take 75,000 and we're going to subtract this 250 times 10 times 10 from it. And that gives us 50,000. So we'll go over here. Equals half of 250 is 125 v sub b squared. So we're going to figure out that v sub b divide by 125 and take the square root, which would give us exactly 20. So 20 meters per second. Now, what about from the velocity at point C? We can do the same thing this time, only we can do it from A to C, or we could go from B to C. It doesn't matter. With energy, what you're going to find is as long as if it's conserved through the whole thing, then it doesn't matter where you start and where you end, as long as you can find. So you've got your choices. So right here, I'm going to go from A to C because that's easier. So we know the kinetic energy at A plus the potential energy at A equals the kinetic energy at C plus the potential energy at C. Well, we know this is 0. We know this is 75,000. We did that already. So it makes my problem easier. 1/2 mv squared plus mgh at C. So this is going to be the same thing, 1/2 of 250. But this time we're going to have the mass, 250 times gravity, but the height this time is 25 at 75,000 over here. So we're going to again subtract and divide by what? 125? So 75,000 minus that 250 times 250. Divide it and take the square root, and we get a velocity of C as 10 meters per second. Okay? All right. How do we apply conservation of energy to springs? What do we do with springs? Well, what do we know? We, of course, know the energy initial is equal to the energy final, right? So now it says, what's the Bow's force constant? So we're actually starting in A with force. So what is the force on a bow? What is that formula? F equals kx, right? Okay. So if we want to know the force constant K, we need to divide both sides by x. So K is going to equal F divided by x. Well, he uses 100 newtons of force to pull a distance of 0.15 meters, which is about 666 repeating. So 667 newtons per meter is going to be your force constant. Now, why do we need that? Because remember, if we're talking about energy, with the velocity in B, we're doing energies. Energy initial equals energy final. Well, what type of initial energy do we have? We have to consider here that we have kinetic plus potential equals kinetic plus potential, right? Or it's final, initial. Well, what types of things do we have here? It's starting at what? 0, because it's holding it still. He's pulling the bow back and he's holding it. So the kinetic energy initially is 0. What does it have, though? What type of potential energy does it have? It does not have gravitational potential energy. It has, because a bow is a stretchy thing, it is spring potential energy. So this is going to be spring. So this is going to be 1/2 kx squared. Now, does it have potential energy afterwards? No, that's gone. It's already been done. That's gone. So now what's going to happen is, so now where's it gone? It's been converted into the arrow. So once the bow unsprings itself, this goes to 0. So this is 1/2 mv squared. So now we have this idea right here. So we can do, the halves go away nicely. We know K is 667. We know X was 0.15, so we're going to square that. Equals the mass, which is what? 0.2 kilograms. That's right here. And times the velocity squared. So now all we have to do is multiply and divide, a few things like that. Multiply, divide, and we should get a velocity of about 8.7 meters per second. Okay? So that's the velocity of the bow. That's all we've got. Next time we will be looking at forces. Those things act. Sorry, this thing is acting funny. Wants to skip around. So here we go. Conservation of energy with pendulums. Well, pendulum problems become a lot easier to solve when we get and look at this change in potential energy for a pendulum. Okay, so what are we looking at now? Calculate the change in potential energy. Well, to calculate the change in potential energy, guys, in part A, we have to know how far it falls. So we're going to say this is our 0 level, okay? This is the ground. So now it's risen to here, so we really need to know what this is, H. So in part A, the change in potential energy is going to be U final minus U initial, which is really going to be mg times H final minus H initial. Well, H initial we said was 0. So really what this is just going to be is mg H final. Okay? Well, what is the final height? Can we find that? Yeah, we can use trig to find it. I want you to think about it. All right, so how do we find that trig? It's angle of right here of theta. So this is actually pretty cool because right now what we have is this. Now, we know this full length right here is L. So we also know that this is L. Those two things are the same. This is L right here, but this whole thing right here is also L. So if I want to find what H is simply going to be L minus this little chunk right here in green. So we got to do L minus whatever that is. So whatever this is, we'll call this Y. L minus Y. Well, we can use trig to find that. We absolutely can use trig to find that. If we use trig to find that, what are we going to see? Well, this is adjacent, Y is adjacent, and L is the hypotenuse, isn't it? So if we've got adjacent and hypotenuse, then we're talking about cosine, aren't we? So this guy is actually going to be L times the cosine of theta. So now we can plug that in. And we're going to take that and plug this in right here. So we know that height H is going to be L minus L cosine theta. So now let's take that and put it in right here. So my change in potential energy is going to be mg times L minus L cosine theta. Okay? Now in part B, it says calculate the speed of the bob at the bottom of the swing. Well, we got to kind of do it before and after. So in the beginning, what types of energy do we have here? So in the beginning, this is our before. I have kinetic energy is going to be initially is going to be 0 because it's not moving. But I have potential energy, gravitational potential energy, and we figured out what that was going to be, okay? That's going to be our mg L minus L cosine theta. Now, after we're at our 0 line, it is going to have potential energy, or I'm sorry, kinetic energy. It's going to be 1/2 mv squared. But gravitational potential energy, since that's our 0 line, is going to be 0 here. And we know that energy initial, we know that the initial energy is equal to the final energy, don't we? So initially we know we have gravitational potential, and finally we know we have kinetic. So this is going to be our mg L minus L cosine theta equal to 1/2 mv squared. Notice something. What goes away immediately? M does. The mass doesn't matter. So we're going to multiply both sides by 2. Multiply this side by 2. So what we have over here is v squared is equal to 2g times L minus L cosine theta. And then we're going to take the square root. So my final velocity of the bob as it hits the bottom point is going to be the square root of twice gravity times L minus L cosine theta. Okay? And then finally, it says in C, it says calculate the tension, maximum tension in the cord. Where is the maximum tension in the cord going to be? It's going to be at the bottom, isn't it? Okay. Okay, so calculate the maximum tension in the cord. This is where Newton comes in. Where's the maximum tension going to be? It's going to be at the very bottom, isn't it? Isn't that where gravity is going to be working the hardest as it's coming down? So at the very bottom, if we were to do a free body diagram here, we know that the tension is straight up and the force of gravity, or the weight, is straight down. So we know the force of tension is going to be equal to the force weight down there at the bottom, which is going to be mg. So that's just going to be equal to that, what? Pendulum bob mass m times gravity. So that would be the maximum tension it would feel. Pushing forward, non-conservative forces. Now, example D here. We've got a block released from rest at a point. It's a roller coaster, looks like, doesn't it? All right, so what do we have here? We've got a 0.1 kilogram block released from rest. So from rest is important now because that tells us what our initial kinetic energy is 0. Above, at point A, at vertical distance h above the ground. So since it's above the ground, that's going to tell us that we have initial gravitational potential energy. Okay. Slides down an incline track around a circular loop of radius 0.5 meters, then up another incline that forms an angle of 30 degrees with the horizontal. Block slides off the track with a speed at point C, which is a height of 0.5 meters above the ground. Okay? Block just barely stays in contact with the track at the top of the loop. Determine the height h. Okay. So how are we going to determine the height h? So what do we know? We know energy initial has to be equal to energy final. We get to pick where we want to have this. I'm going to pick point A. Initial energy is at point A, and then I'm going to pick C because I know something about it there, and I'm going to pick this at C. All right, so there's my beginning and ending point. So I'm going to start here, and my after is here, at least for part A. Okay, so in the beginning, I know I have gravitational potential energy, and in the end, I know I have what? Both gravitational potential energy and kinetic energy. Okay? Because it's above the ground and it's moving. Well, how fast it's moving do we know? We do not know, do we? Now it wants us to find, oh, so we are actually kind of in trouble here. We can't do it this way. We can't have it go through at this track in this particular direction. So what are we going to do? Well, let's regroup and think again. So we can't use C because we don't know the speed at C. As a matter of fact, we'll use this formula for B. So what we have to figure out is, what do we know at A? What else do we know? It says the block barely stays in contact with the track at the top of the loop. Okay, that should tell us something. You know what that tells us? That tells us we have no normal force. That at the very top of the loop right here, when the car is sitting right here, let's look at that. That means we have only centripetal force. So our sum of forces right there, which is going to be equal to what? So I'm going to find that first. Is going to be equal to ma centripetal, which is mv squared over r, which I know all of those things. I know this is 0.1. I don't know my velocity, but I want that. And r is 0.5. So that has got to be equal to what? What's the only thing acting on it at that point? Gravity. mg. So if you think about it, if it's barely touching, we only have the force of gravity acting here. There's no normal force here because normally there would be a normal force, but because it says barely touching, barely in contact, that means this goes to 0, doesn't it? In that particular part of the question. All right, so it's just mg. Well, that's cool because now we can take 0.1 v squared over 0.5, set it equal to 0.1 times what, 10? Well, this 0.1 and this 0.1 go away. So we get v squared equals 5. Take the square root of both, and we get a velocity that's what? Let's see. Working this out. About, what, 2.24 meters per second at that point. So now, why did I do that? Well, because now I can use that to figure out what's going on, because I know what the potential energy is. I know that it's got kinetic here and it's got potential here. So let's set the problem up and actually figure this out. So if we do E initial equals E final, we said K initial plus K final plus U initial here. K initial is 0 because this is at point A. This is going to be the top of the track, top of the loop. At the top of the loop, we have potential energy and we have kinetic energy. So let's figure this out. This is mgh. This is going to be mg at the top of the loop is what? The h here is going to be, we've got 0.5 and another 0.5. So this whole thing from here to here is going to be 1 meter. So this is going to be times 1 plus 1/2 mv squared. So let's plug everything in. M's go away. All my m's go away. It doesn't even matter about that. So we've got 10 times h equals 10 times 1 plus 1/2 that velocity, 2.24 squared. So we have 10h equals 10 plus, that's really the square root of 5. So 5, half of 5 is 10 minus 2.5. So h is 0.75 meters. All right, so where did I make my mistake? Ah, I see it right here. Should be plus, shouldn't it? So this is 12.5 divided by 10, which is what? 1.25 meters. I knew it couldn't be 0.75 because that would be lower than the circle, top of the circle. All right, so we have part A. Now, part B, we said we were going to determine the height at point C. So now we're going to do the energy at A has to equal the energy at C, if you want to think about it that way. So the energy at A is still that mgh, and that's going to be equal to 1/2, because at this point we've got 1/2 mv squared, and that's plus mg and the height at C. So this is the height at A, and that's the height at C. So what do we know? So this is going to be m's going away again. Didn't matter about the mass. So we have 10 times the height, which is 1.25, plus 1/2 velocity at C squared, plus 10 times the height at C. The height at C is only 0.5. So we have 12.5 plus 1/2 velocity at C squared, sorry, equals, this should be equals, and this should be equals, plus 5. Subtract, multiply by 2, Divide, so we're going to subtract 5 from both sides. This gives us 7.5 equals 1/2 velocity at c squared times both sides by 2. We get 15 equals velocity at c squared. Take the square root. So we're going to take the square root of 15, which is 3.87. So we get a velocity at point C of about 3.87 meters per second. Okay? So that's B. C, determine the max height above the ground attained by the block after it leaves the track. Okay. Well, now we're going to do same kinetic energy thing. We don't have to use kinetic and potential energy. We don't actually have to use kinematics anymore, because what's going to happen is this thing's going to keep going, and we want to figure out what is this height right here. Height final. We don't know that. But what we do know is that it is going to do what? Well, let's figure it out. Well, it's going to take a little kinematics right here, because this is the 30-degree angle. Think they gave us that for a reason? They did. Because what we know is we know the velocity here. That velocity is at an angle. Well, at the very top, we know we're only going to have a velocity in the x direction, because the velocity in the y direction, if you remember, projectile motion is 0. So we need to find the velocity in the x direction, which is going to be this velocity v at c times what? The x component, which will be v sub c cosine of 30 degrees. So we know that. So let's find that. So velocity in the x direction is going to be equal to, this is our final spot, is going to be v sub c cosine 30 degrees. That means it is going to be what? 3.87 times the cosine of 30 degrees. So I'm going to take that 3.87, multiply it by cosine 30, and I get 3.35 meters per second. Okay, so there's my final velocity in the x direction. So now I'm going to do energy initial equals energy final. And it really, again, does not matter where you start it from. I can go from A all the way to the very end. So let's do the energy at A equals the energy at that final. So we know this is, again, kinetic energy at A is 0 plus potential energy at A equals kinetic energy at the final plus potential energy at the final. Okay? Now, we already figured out what U of A is. If I remember correctly, we figured out right here our potential energy is 12.5. So let's go ahead and just plug that in. 12.5. Kinetic energy is 1/2 m. Well, the mass is 0.1. So this is 0.1 times that velocity squared, 3.35 squared, plus mgh. So this is 1/2 mv squared. And this is going to be our mgh final, right? mv final squared. So m, which is 0.1, times g, by the way, this is times 0.1. I forgot. When we did this over here, we got rid of m. So we better put that m back in, even though I'm going to cancel it out again. Times 10 times the final height. So again, I can get rid of mass. So I have 12.5 equals half of 3.35 squared. Which is about 5.625. plus 10 times the height final. So we're going to subtract 12.5 minus that 5.625, and then we're going to divide by 10. And we get a final height of approximately 0.69 meters. Okay, 0.6875 meters. So there's my final height. So we're going to be, so now that's it for conservative forces, introducing the idea of using work and energy when we have things like friction that make it easier to solve those types of problems. All right, you need to work, at this point you need to be working on, or in class you'll be working on 4.3 exercises next time. So make sure you look at these notes again.